Everything fine?
Yes, sir. Yeah.
Okay, very good. I have to get used to doing these things via Zoom. It's so much nicer if you have the screen right here. It's so much simpler. But of course, I understand that people outside are also going to watch. It makes a lot of sense. And if you record, but you're recording, yes, yeah. Okay, so thank you for the opportunity. Those who heard the talk yesterday, I'm afraid there's going to be quite some overlap in the with what I talked about in the seminar, but I will go much more into depth today. And what I will be talking about is quantum sensors linked to particle physics. Now, you've been hearing a lot about high energy physics.
Just one small, I think yesterday, no student were in this lecture. So
Sorry?
yesterday, students were not.
Yes, exactly. Yeah, no, don't worry. I'm just warming up. That's all. But some people were sitting in the lecture yesterday. So I'll be talking about applications of quantum sensors to high energy physics, but also to low energy physics. And I will explain, of course, quantum sensors are naturally linked to low energy particle physics. There's a lot of reasons why they're being used there, and I'll talk about their potential. But I'll also, in the second half of the talk tomorrow of the lecture, go into how one can apply these very sensitive devices into a regime where normally that you would not expect them to be functionally appropriate. So I'll say some words about the landscape, how these approaches fit into the overall approaches of particle physics. I'll talk about clarification of the terms, what I mean with quantum sensors, and then I'll talk about quantum sensors for low energy particle physics, for new low energy particle physics experiments that are being thought about right now, but that are not currently possible, but where quantum sensors might play a role. And then I'll talk about high energy physics applications. And a lot of what I talk about is speculative. So if you're coming here to learn about what is being done and what is possible right now, forget about it. This is speculation. In many cases, it goes well beyond what we know works, but it indicates directions that might be worthwhile pursuing in the coming years. So first of all, let me say what I mean by quantum sensor. For me, a quantum sensor is a system that registers, oh, is this off? That registers a change of a quantum state caused by the interaction of the sensor with an external system. So for example, this can be a transition of a system between a superconducting state and a normal conducting state. That's a quantum transition. It can be a transition within an atom of one energy level to another, or it can be a change of resonant frequency in a quantized manner within a cavity. And if one uses that kind of approach, then a definition that works quite generally is that a quantum sensor is a device, the measurement capabilities of which are enabled by our ability to manipulate and to read out its quantum states. So you have a way to set them up, to change them, and to record what the quantum states of your sensor are. And normally, a quantum sensor is highly sensitive, which means that the energy transitions are minute, which means that, unsurprisingly, quantum sensors are ideally matched to low energy particle physics. I'll talk about that mainly, but I'll also talk about high energy particle physics, how you can use these in spite of the fact that the energy scales are not commensurate. What I will not be talking about is entanglement. And in a way, this is a shame, because entanglement is at the heart of quantum sensors. However, potential applications of entanglement to quantum sensors are only in the starting blocks in the case of low energy particle physics, where they do provide a gain, and nobody's come up with any good ideas yet how to use entanglement for high energy particle physics detectors. At the end of the lecture tomorrow, I will ask you to come up with ideas. I haven't managed, no, my colleagues haven't managed either, but I'm sure you will. So the technologies I'll be focusing on, and I'll talk about today, are these here. And that's only a subsample of all possible technologies, but you can sort of regroup the kinds of sensors that people are working with these days into these categories here. And these are large families, so they're not individual technologies, they're families of technologies. Superconducting devices, and I'll say more about that, transition edge sensors, superconducting nanowire single photon detectors, but also the infrastructure surrounding it. There are amplifiers, cryoamplifiers, capacitors, devices that work at the temperatures at which the superconducting devices themselves work. Then there's the family of spin-based devices, devices that are sensitive to spin of a system. And one of these in this family are nitrogen vacancy diamonds. And I'll say more about that also. These are crystals, diamond crystals, where one carbon atom is replaced by, for example, a nitrogen, and where one can manipulate and read out the state of this one nitrogen atom within the crystal matrix. And that is a very sensitive magnetometer. Then there's the whole family of optical clocks, and I'll say much more about that as well. Many of these optical clocks actually have a close link to ionic, atomic, and molecular system, but they're also nuclear clocks. Then furthermore, optomechanical sensors, sensors that are sensitive both in the optical regime, but also in a mechanical regime to vibrations, where you pick up vibrations through optical transitions. And then a very large category of materials that are engineering of materials at the atomic scale, where you intentionally construct devices atom by atom in a way. And the linked materials of 0, 1, and 2-dimensional materials, which is a single atom or small, minute clusters of atoms like nanocrystals, linear crystals or linear structures, and monolayers of molecules. And with these devices, one can cover a wide range of physics that is of interest to particle physics. One can, of course, search for new physics and beyond the standard model physics. One can look for axions, axion-like particles, dark matter, but also non-dark matter, ultralight particles. One can test quantum mechanics itself. This is a very interesting field in its own right. In particular, the questions of how the wave function collapses and how decoherence happens. And one can test fundamental symmetries, for example, looking into electric dipole moments of particles. Now, the question, of course, is why does this work and why do quantum sensors allow you to do this? And the reason for that is that depending on what you're looking for, very light dark matter particles like axions or axion-like particles are large. Their wave function is not that of a particle, it's actually that of a very extended wave or a field. And so you can really think of these as classical fields in some cases. If you're looking for very light axions, you should really be thinking about how to measure an electric field or a magnetic field that is constant in this space-time here in which we're sitting. Axions and axion-like particles in QCD can couple to the magnetic field, to the outside magnetic field via this Lagrangian here. So you can detect gradients as pseudomagnetic fields, and you can then measure these or detect these, be sensitive to them by thinking of your quantum sensors as atomic magnetometers. You can also look for scalar fields in the same way, because these scalar fields then allow you to be sensitive to variations of fundamental constants, or vice versa. If you're trying to measure variations of fundamental constants, like the electromagnetic coupling, you're then sensitive to these scalar fields indirectly. And finally, you can measure the symmetry violations that I mentioned before via precision measurements. And the symmetries you're looking for are symmetries that are fundamental to our standard model. These are symmetries like CP violation, CPT violation, Lorentz invariance violation, the weak equivalence principle, and all of these actually have been characterized in a single extension to the standard model called the standard model extension, which allows one, by doing precision measurements, to exclude these different symmetry breakings in a way that is comparable in different systems. If you do an atomic measurement, if you do a neutron measurement, if you do a CP violation measurement in K0 decays, these can be compared in the framework of this model. So let me go through the individual technologies and say a few words about each of these technologies to give you a feeling of where one is right now and what their characteristics are. And I'll start out with the first family, the superconducting devices, the transition edge sensors, the single superconducting nanowires. These are under very active development. The first devices appeared around 1990, and these are the transition edge sensors. They're basically a superconducting device that switches from being superconducting to being normal conducting. And you can very quickly go from this to the kinetic inductance detectors, which have a similar transition. You go from being superconducting to normal conducting, but now you're sensitive to photons that break the Cooper pairs of the superconducting and create excess quasi-particles. And this kinetic inductance that you then create of the superconducting strip is then inversely proportional to the density of the Cooper pairs that still are around. So as you absorb photons, you have less and less Cooper pairs. That allows you then to be sensitive inside an RC circuit that allows you to form a microwave resonator. And so actually what you're doing is you're measuring the frequency of this resonator where you're using the superconductor as part of your circuit. That allows you to measure how many photons you've been absorbing. And that approach then goes into the traveling wave parametric amplifier, which has been around since about 10 years. And you can go to the most recent developments, which have to do with the superconductor spin system quantum memory elements. So if you look at what these different technologies, I've listed a number of technologies here that are in use right now, what they can do in terms of detecting photons. You can see that for the standard photons in the optical regime, from the far infrared to the UV, you can use any of these technologies here: transition edge sensors, kinetic induction devices, superconducting nanowire single photon detectors. But if your photons are not in this regime here, but actually in much longer wavelength, sub-millimeter, far infrared, or even microwave, you can see that these newer devices here are actually appropriate and allow you to extend the range in which you are sensitive. And you can even use some of these technologies, in particular the transition edge sensors, for high energy particle detection. And this is one of the things I'll come back to tomorrow at the end of my lecture, showing how one can use transition edge sensors as a detector for high energy particles, even as a tracking detector. To give you a feeling for what these devices have been going through in the last 2 decades, this plot sort of summarizes what progress has been achieved. And a way to measure the progress is in terms of the resolution that you get when you're trying to determine the energy of a photon. This is the energy resolution in electron volts in the last 40 years. And you can see that as you go along, each of these now has reached levels where you can get down to electron volt resolutions for full width half maximum. Although normally you start out with much, much higher resolutions here. So since about 10 years, the average energy resolution, or the best energy resolution that can be achieved, is around an electron volt. And this is independent of the technology that you can use, which means that if you want to do precision X-ray imaging with high resolution, X-rays being of the order of 10 keV or above, you can get energy resolutions down to far better than ppm. 10 to the minus 5 is what you get here with this kind of setup. So an energy resolution at the order of an electron volt at 10 keV or a few keV has been done already since a few years, and there's no reason why this should not continue increasing. These are very, very precise and sensitive detectors for precision measurements. I'll say a few words now about these two categories, the spin-based sensors and the optical clocks. They are complementary in a certain way, but what they're both trying to do, or what they're both used for, is to try to measure the changes in the environment. Remember, I said that many of these low energy axions or light particles are actually changes in magnetic fields or electric fields. So what you're looking for is changes over time of some field strength. This coupling is one way to look at this, but the absolute strength is the same. You can look for oscillations, periodic oscillations, which would stem from interactions with very light dark matter as this wave goes through. You can look for fast transients of any measurement that you're capable of doing, which allows you to search for dark matter and topological defects. And you can look for drifts in fundamental constants, like the electromagnetic coupling constant, over time. And any drift of fundamental constants means, of course, that they're not constant, which has to be a sign of new physics. to do that most precisely, you benefit from setting up networks of sensors. If you have a single sensor, of course, you're going to be sensitive to the environmental noise at that point. But if you have a network of sensors distributed and that are connected to each other, then you can use the measurement at each individual point to cross-check all the others, but also to be sensitive to variations across the network. It allows you to do directional measurements of changes. For example, when a wave sweeps through the Earth, different sensors will react at different times in different modes, if you're looking for oscillations or transients or drifts. And this means that setting up networks of sensors measuring magnetic fields or the constants themselves, like in atomic clocks, or optical fiber networks that allow you to connect and synchronize different points, allow you to investigate very light scalar and pseudoscalar dark matter candidates over many, many orders of magnitude. And these are the kinds of experiments that are being done right now. This is, for example, a network that is looking for spin-based changes. So it's a network of optical magnetometers spreading around the globe and looking for things like a topological defect passing through the Earth that will change the measurements over time in the different measurement points. So what you get here is, for example, an axion-like domain wall passing through the Earth, which means that you have simultaneous and correlated signals among the different detectors. And you can then use this to measure transient magnetic field pulses at the sensitivity of these spin sensors, which have a resolution of picotesla. So you have an extremely sensitive device that allows you to eliminate noise and malfunctions of the individual sensors. But even more importantly, if such an axion-like particle domain wall passes through, it allows you to measure the directionality and the transition speed. You can do other measurements of spins with, for example, a ferromagnetic particle that you levitate over a superconductor. You cannot see it itself, but it's actually sitting right here above this niobium superconductor. You have a small levitated particle that you then observe with optical means, interferometric means that you can then use to see any movements. So this sensitive ferromagnetic particle is going to move around if the magnetic field changes. Or you can look for exotic spin-dependent interactions with a nitrogen vacancy structure, which is a spin-sensitive sensor that is sitting on top of a, so within a diamond plane that you observe with a probe here that you can move around. So this probe can approach and move away from your sensor, and you can look for exotic interactions between this object here and this object here that you can measure very precisely and, importantly, probe at very small distances. So you're looking for exotic interactions at very small distances with these detectors. Optical clocks allow you to measure something else. They allow you to study the variations of fundamental constants like alpha, or the ratio of the proton to electron mass. And the interesting thing is that different atomic systems have different sensitivities to these two numbers, because, of course, the composition of the nucleus is going to be different. The energy levels are going to be different. And if you look in different types of clocks, so here is a range of different clocks, then you can see that in each of these different clocks, you can reach sensitivity to alpha electromagnetic and to this mass ratio that are different. And by looking at these many different systems, you can reduce any systematic uncertainties that you have from calculations to very low levels. You'd like to entangle these, and entanglement between measurements at different places has already been carried out. The benefit that you get from entangling two different atoms that you're measuring is that you get a factor of about 2 currently in improvement in resolution over the measurement of a single system. But of course, what you'd really like to do is have a network, a super stable global network of clocks synchronized with entanglement. And this is something that people are thinking about, but that hasn't actually happened yet. We need more measurement schemes. We need this kind of network to actually go beyond what has currently been looked at to improve the sensitivity and to get to the point where maybe you discover something unexpected. The sensitivity is currently about here. An improvement in sensitivity by a factor of 1,000 within a decade should be feasible in these different clock schemes, and a factor of 10 to the 7 on a time scale of 20 years. So by the time you're professors, hopefully these measurements will have improved over the current sensitivity by about a factor of 1,000,000. The first networks are being set up. These are just local networks within the UK. There are networks within Europe that are being set up currently, but as you can see from the dashed lines, they're not yet very complete. This is something that's actively being pursued right now, but that's not in place yet. But if you have these systems, then you can do measurements in a number of atomic systems, but also in other related systems. So not only atoms allow you to measure very precisely, but also things called highly charged ions, where you've basically removed a certain number of electrons from an atom. For example, argon 18, if you remove 13 electrons and 5 electrons remain, then argon 13 plus looks just like boron, except for the fact that because of this very strong electric field that you have, because you have such a strong charge, the energy levels of the boron system are going to be shifted from the microwave into the optical for the hyperfine splitting, and from the UV light, 250 nanometers, into the extreme ultraviolet of 20 nanometers. So this transition is probably not going to be easy to measure, but this transition is, because you can use the full mechanics, the machinery of precision optical transitions to then measure hyperfine splitting. And that allows you to look for Lorentz violation searches, variation of fundamental constants, dark matter searches, tests of QED, and fifth force searches. You can also use these kinds of systems in a different way by combining them within a molecule. So you have, instead of a single atom or nucleus with an electron or several electrons, you have two systems, a positive charge, a negative charge here. And between these two poles of a molecule, the electric field is extremely strong, already normally for spherical nuclei. But if in addition you replace one of these nuclei by, for example, radium-225, which has a natural pear shape, then you enhance this electric field even more. And what you try to do with that then is to measure the hypothetical electron's electric dipole moment, which in the standard model is immeasurably small, but which induces, depending on this, the orientation of this electric dipole to the electric field inside the molecule, a splitting of the energy lines that I mentioned just here, you can be very sensitive to. That's a way to measure this electric dipole moment of the electron. One of the limitations of these systems is that you're going to be sensitive to any temperature broadening, any smearing, Doppler smearing of a transition in here. So what you'd like to do is cool these molecules or these systems down to very low temperatures. Laser cooling of molecules is not trivial, but laser cooling of multi-component molecules, so binary molecules are hard to cool, but multi-component molecules might be easier to cool. In a system like ytterbium oxide, OH, you could be able to cool one component while then measuring on the other one. And that should allow you to achieve much higher sensitivity on these electric dipole moment searches. Similarly to temperature, time is also an important variable. The longer your excited state lives, the more precise the transition can be measured. And one of the most sensitive systems to think about is the isomer of thorium-229, which has a lifetime of 5,000 seconds. And so naturally, a very narrow transition and a very natural transition between the isomeric state and the ground state. If one could measure this transition to its natural line width, one could achieve a precision of 10 to the minus 20 on this transition here. The problem is that currently, this is the only nuclear transition that is known in the optical regime, and it's only known to a few percent. In order to do laser probing of this transition, you already have to know it to a PPT level. That's where lasers start kicking in. So a lot of work still needs to be carried out to characterize this transition from mass measurements currently, which are being used to measure the difference in mass between the isomeric state and the ground state. So it's really an energy measurement via mass measurement, to the point where you can actually probe this transition with a laser. This is something that's ongoing right now. Just very recently in 2021, this percent resolution has been achieved. Much more progress is going to be needed, and possibly one will need a different way of making this isomer in a larger quantity, because the current production schemes rely on radioactive decays to produce it. But in all of these cases, what one can see is that the relative precision of these clocks that are being produced has dramatically improved. And if you look at the precision that's currently possible, it's at the level of 10 to the minus 18. This is a plot from 2015. It's already improved with respect to that. And one can look at a large number of possible clocks that are being looked into. I talked about the highly charged ions, atomic nuclear clocks, but you can also think about molecular clocks. Also, these are playing an increasingly important role and to allow one to achieve precisions that continue to push this sensitivity to new physics, as do optomechanical sensors. So I'm coming to the fifth technology now. What you're looking for is wave-like dark matter, so extended dark matter objects, which, depending on whether the nature of this wave-like dark matter is scalar-like or vector-like, good detectors can either be optical cavity-based detectors or accelerometer detectors. For extended object dark matters or particle dark matters, but also for gravitational wave detection, you can use similar devices. And so one of these devices that you can think of is to compare two cavities with each other, two Fabry-Perot cavities, where you have one that is rigid, that is not going to change as you go through a changing external field, and one is free to move, and you're looking for the strain between these two objects. This allows you to measure the interaction with ultralight dark matter in form of a variation of the atomic size. So you're really measuring the strain that you see in this rigid spacer and comparing it with the cavity size in here. The accelerometer side of things is equally interesting. What you do here is you can build a structure, a very small structure, where you have different compositions. So in this case, you have a very tiny cavity, a beryllium bulk covered by a thin silicon nitride membrane. And you're looking for changes of the, you're looking for acceleration, differential acceleration between these two objects of different composition. So what you're doing there is probing couplings that go well beyond the standard model, couplings that would couple to baryon number or to lepton number. And in a structure like this, you can reach very high precision, well beyond what has been achieved in previous searches for baryon minus lepton couplings by, for example, the Ötwasch experiment. But because of these, the way these structures are built, they have a very high sensitivity to a specific dark matter mass. So their resonant frequency is extremely well defined. And if you want to probe different points inside your parameter space, you have to basically be able to build dedicated narrow band or high resonant frequency structures with different dimensions. Now this kind of approach, while being very sensitive, does not scale very well. You cannot build a detector that will cover a wide mass range. In a similar vein, and so again, as I was talking about before about floating a magnetically sensitive device, you can also try to levitate microspheres inside a vacuum vessel, inside a cavity. This is a single microsphere that is levitated inside this device here. And these devices are sitting inside a crystal, an optical lattice in a way, which allows you to look for movements of this massive object. So this is not a single particle anymore. This is already a relatively large object that allows you to be sensitive to very weak forces that an external field exerts on it. This external field can either be very high frequency gravitational waves coming from example from primordial black holes or from axion fields, but also from other devices. And it even allows you to be sensitive to dark matter, to massive dark matter, moving relatively slowly. So think of this as being a dark matter object, a dark matter nugget, something very massive, moving along at a relatively low speed of a few hundred kilometers per second, passing by this levitated sphere. As this object passes by, this sphere is going to be deflected or attracted, and you can try to measure the movement of this levitated microsphere as a function of time. And this allows you to search for composite dark matter in a relatively sensitive manner for specific types of dark matter objects. But if you take this to the next step, you can think of actually building an array of these. If you think of a three-dimensional object where you have multiple suspended nanospheres and a dark matter particle comes flying through, as this dark matter particle goes through, the individual suspended nanospheres are going to be attracted and then relax back into their position again. They're each at the bottom of a potential well, and they're pulled up the potential well, so then they will come back down again. And you can think of this as a three-dimensional object that allows you to see the passage of specific types of dark matter particles as they go through. This is what is called the wind chime experiment, where you need something like 1 billion detectors with an overall mass of around a gram. But with that, if you can build something like that, so suspend 1 billion, which is maybe not so hard because you need to have 1,000 times 1,000 times 1,000 suspended nanospheres, then you become sensitive to Planck scale gravitational dark matter detection. This is one of the few detectors that actually allows you to go all the way out to the Planck scale. And then the last category that I'll mention are the metamaterials and the low-dimensional materials. The metamaterials are materials that are engineered at the atomic scale. So their structure is composed, sorry, their properties are defined by their structure rather than the material from which they're composed. And you can build different structures. So with standard silicon modification technologies, you can build multi-composition structures. You can build geometric structures that consist of circles, of crosses, of different densities of materials of different types across the surface. And depending on which kind of geometry or composition you choose, then the absorption of light by these objects is going to be very different. So this structure here, for example, has absorption resonances at in the near infrared, very near infrared, and the mid infrared. This structure here is sensitive to polarized light for specific frequencies. This will absorb in a broadband in the far infrared. And this one here is actually going to absorb even in the optical regime in a broadband manner. So basically devices like this are excellent calorimeters. They will absorb all frequencies of light more or less evenly. And the important message of all this is the properties can be designed. You just have to be clever about how you design your device, and you can achieve whatever property you would like to have. I talked about broadband absorption, but you can do the same for narrowband absorption. A structure like this one here will allow you to very carefully, by careful tuning of the sizes of these individual cylinders, their height and their separation, achieve a very narrow band absorption for a specific frequency here in the near infrared. In the same time, the reflection outside of that specific frequency is going to be excellent. So you have a mirror that is basically only going to absorb a specific color. And this can be used very well for the design of circuits, but also for other detectors. You have, so this is geometric tunability, but you can also design devices, for example, by combining graphene with a dielectric, generate a tunability that is electric. So you can tune the device continuously as you're working with it. and change the absorption frequencies and the reflection frequencies as you wish. And you can get to the point where actually you can get a perfect absorption of light by having, for example, a structure of a reflective metal substrate, a dielectric, and then on top of that, patterned graphene microribbons, where you choose then the separation, the width, and of course the thickness is given by the monolayer of graphene. And this is a perfect absorber then. The freedom that you get from that is that you can build a detector to do anything that you want and absorb anything that you want. Now, I'll talk about 0 and 2-dimensional materials tomorrow, so I'll only mention very rapidly the 1-dimensional materials here. These are often used in superconducting devices. So as, for example, a 1-dimensional junction Josephson escape sensor, which is really just a transition edge sensor, but at the nanoscale. And this is again suited to detecting dark matter or axion interactions with electrons. And what you basically have is a very low thermal inertia device that is very, very easy to excite from the superconducting state into a normal conducting state, and where you can then pick up any signal via the voltage drop between the two leads. So it allows you, if you build this correctly, to even do directional detection of light dark matter, because the dark matter scattering inside this 1-dimensional device produces excitations which have an anisotropic distribution. And that anisotropic distribution allows you then to look at the orientation of the dark matter particle with your device. And you can build very large structures. This is, for example, a 400 micron by 400 micron device of these superconducting nanowires with extremely low thresholds, so sub-electron volt energy deposition thresholds. And that allows you to measure over a large mass scale or search for over a large mass scale for specific types of dark matter. So with that, I'd like to now come to real experiments, how to use these devices in real experiments. And one of the areas one would like to pursue has to do with the search for axions and axion-like dark matter. And up to now, looking for dark matter has concentrated to a large extent to searching for weakly interacting massive particles at high energy detectors, and looking with resonant cavities for light axions in a specific mass range where these resonant cavities, these microwave cavities, are particularly sensitive. But one would like to be able to fully cover the whole parameter space of possible masses. And there one has to think about what the figure of merit that a axion detector has means for the construction of these devices. So the figure of merit is defined by the coupling of the axion to photons squared, the mass of the axion squared, the fourth power of the magnetic field, which gives you the axion photon coupling that then allows you to detect this photon here, the volume of your detector squared, the temperature of the device to the inverse second power, and the quality factor. And what you'd like to do is optimize everything so that you can get the highest possible sensitivity, but there are going to be trade-offs. And I'll explain one of the trade-offs afterwards. To cover this regime here, different experiments, I'll briefly talk about dark matter radio and Casper and electric nuclear magnetic resonance experiments here, cover this mass range down here. So mass range is one thing, but the sensitivity is the other one. The standard model axion would lie somewhere on this line here. So whatever you do, you need to try to get close to this line here in terms of your sensitivity at a certain mass, which means that as the mass goes down, you have to become ever more sensitive in order to have a chance of detecting a signal that could correspond to the standard model. So different approaches are spin-based nuclear magnetic resonance, microwave cavities, and bolometers and transition edge sensors. Dark matter radio is really that. You can think of this axion field as being an electric field that moves up and down, and you're trying to detect that signal via your radio. So as in a normal radio, you have a resonant circuit, a pickup coil that couples to the axion field, and you look for the signal that comes through this resonator. And with that, with this kind of approach, large volume devices of 50 liters or cubic meters allow you to cover a wide mass range, but not quite reach or only optimistic, only for the highest masses of axions, reach the standard model expectation. If you want to go to other masses or other ways of looking for axions, you can use the fact that these axions can couple to the spin of a device. So if you look for the spin in your apparatus, you would couple via this, or you can use the fact that the spin couples to the axion gradient. And so this is the other way of looking for that. In both cases, what you're looking for is a spin change, or you use a spin sensor to measure the presence of an axion field. And so you need to have a device that allows you to measure the nuclear spins inside your apparatus, and that couples the axion field through a pickup coil to that. Currently, only a very narrow mass range can be excluded with this approach here, with this NMR approach, but you can improve this quite significantly still. I'm not going through the details because the slides will be available if you want to follow up. But what I wanted to point out here is that these approaches allow looking initially already at a phase space that hasn't been explored before. And that as one scales up these systems, as one addresses engineering challenges, improved devices with vastly expanded phase space will become possible. And in the following, I'd just like to say a few words about where one is on these different approaches. I've already mentioned the highly charged ions, and I'd like to quickly say why these are so interesting for tests of QED and for symmetry violation searches. If you look at these HCIs, I already showed this plot here. The reason for these shifts is really that the transition energies inside the system scale very strongly with the nuclear charge. And as this charge increases, the binding energies scale as the charge squared. The hyperfine splitting scales as the cube of the charge. QED effects scale as the fourth power of this charge. But the Stark shifts, and this is the sensitivity to external electric fields, scales as the -6th power of the charge, which means that if you're trying to measure effects that go beyond QED, for example, you don't need to worry as much in a system like this about external influences. External electric fields are not going to influence your measurement because of this very strong suppression of its sensitivity. I've already talked about the EDMs, nuclear clocks, molecular ion clocks, but what I have not yet talked about is new systems that don't exist yet. And I'd like to say a few words before coming to the end of this lecture about possible systems that one could build and work with in the coming years. And these new systems can be built, for example, through a gateway of antiprotonic atoms, which then allow building and constructing novel highly charged ion systems. And the way this works is that you start out with a normal atom where you replace one of the electrons by an antiproton. This has been done already since 40 years. You shoot antiprotons into bulk matter. The antiprotons are captured into this atom. As they are captured and replace the electron, they then cascade down. There's no Pauli principle to stop them from cascading all the way down to the ground state, which, because of the very large mass of the antiproton, is actually at the surface of the nucleus. The electrons on the way down during this cascade are ejected by Auger ejection because the antiproton transfers part of its transition energy to the electrons. So what you end up with is an annihilation of an antiproton on a bare nucleus. And this annihilation will remove one nucleon, a proton or a neutron, and leave behind a fully charged, a fully stripped nucleus. Because this is a peripheral annihilation, this nucleus is going to have relatively low transfer momentum. And because of its very high charge, it means they can actually trap it inside a Penning trap, just like those that are being used for highly charged ions up to now. Now, using a technique that we developed a few years ago by interacting a nucleus with Rydberg excited positronium, so an atom made of an electron and a positron that is in a highly excited state, allows one to form Rydberg atoms. So we produce antihydrogen this way, but this same technique allows you, or should allow you, once we get it to work, to form Rydberg atoms of a completely stripped nucleus. And this is just a hydrogen-like atom. There's no difference between this and hydrogen, except that the charge is now dramatically larger, and that when you have one electron in here, you still have the remnant charge -1. So this is a highly charged ion, but it's also a hydrogen system. Very simple spectroscopy, very simple to calculate. And doing spectroscopy in this system should allow you to reveal any beyond the standard model effects that you will also look for in other atomic transitions, but with a much higher sensitivity. Now, I talked before about baryon and lepton couplings. You can think of probing them as well by replacing the electron with an antiproton here. Because the antiproton has the same charge as the electron, if you replace this positronium with an antiprotonic atom, like here, that is in a Rydberg state, you can also transfer an antiproton into this Rydberg state of this hydrogen-like highly charged ion. And so you can do precision spectroscopy on these as well and look for baryon minus lepton couplings. You can take this further by then looking for normal Rydberg atoms where you replace an electron by an antiproton and look for these transitions here to expand on going from an atom, working with an atom to working with a molecule. If this Rydberg excitation here doesn't happen in an atom, but in a molecule, then I can transfer one of the electrons into a molecule and replace that electron in the molecule by an antiproton. And what this means is that I now have a molecular system that looks very like the thorium fluoride that I talked about at the beginning, where one looks for an electron electric dipole moment. But now I have the possibility of looking for the antiproton's electric dipole moment, which is something that nobody has tried to measure up to now. And because we have a very sensitive device, we can probe this with lasers, this might be a more precise measurement than can be done for protons. For proton, if you're looking for an electric dipole moment, you cannot build it into an atomic system. You have to actually produce individual protons in an accelerator and look at their sensitivity to electric fields as they go around. Atomic techniques are much, much more sensitive. So this might be a situation in which going to an atomic system, a quantum system, will allow you to be more precise than you can be in standard particle physics. And if you think about how to extend this system, you can go even further by having a dual Rydberg system where you park one antiproton in a first Rydberg orbit, a second antiproton in a second Rydberg orbit. The nucleus will still be able to hold both of them. Because they're in Rydberg states, these are long-lived systems. And here you are sensitive now to the electric field generated by the one antiproton here and the nucleus on the other side, so that rather than being peripheral, the antiproton here is now central and feels even stronger electric fields. And you can take this even one step further by sticking one of these antiprotonic highly charged ion Rydberg atoms next to an anionic system, a normal atom with an extra electron, which again will generate a very strong electric field between the two. So these are systems that have yet to be built. We don't know whether they can be built, how easy they will be, but they hold the potential to go beyond what we can currently do with measuring properties of particles. Now, these atoms also have one further interesting property, which is that they can lead to a new technique, a new way of looking for dark matter, for specific types of dark matter systems. And these are candidates that are called sexaquarks. So this would be a UUDDSS bound state with a mass of around 2 times the mass of the proton. That was proposed by Glenis Farrar a few years ago. And there haven't been any prior searches for this mass candidate. It's not excluded by astrophysical bounds. The problem with this candidate is simply that it hasn't been produced. It was very difficult to produce because you need to find a way to combine 6 quarks in a dense space. So one way to do that is by looking at heavy ion collisions inside the LHC. And in fact, this was a proposal to look for this candidate by looking inside LHC collisions. But of course, a small, low mass particle like this escapes without leaving much energy, without carrying away much energy. So it's extremely difficult to detect. This technique here, on the other hand, allows to produce it at rest with a unique fingerprint, a unique signature. And the idea here is that one forms an antiprotonic helium-3 atom. So this is the quark line picture of these, the system here, where you see the protons, the neutron, and the antiproton. And then the annihilation process happens at the quark level. A DD bar and a UU bar annihilate, form gluons, which can then hadronize again in form of SS bar pairs. And because all of this is very compact, these S quarks here are in the immediate vicinity of the U and the D quarks of the original nucleus. And so they can actually condense to form this sexaquark state. The remaining quarks and antiquarks recombine in form of mesons. And in this particular case, all the resulting quark lines produce a K+, and a pi minus. So a strangeness 2, charge -1 final state with a missing momentum. The kinematics is completely constrained because this annihilation here happens at rest. And so if you try to reconstruct this invariant mass or this missing mass here against which this these three mesons recoil, you find that you get a very clean signal here. This is, of course, a simulation. I'd love this to be a real measurement. But if this state here is produced at a level of 10 to the -8, this is my last slide, so actually I'm fine. If this is produced at a level of 10 to the -8 of all annihilations of antiprotons on helium-3, then one would see this signal here. And this is the background that we expect based on standard annihilations of antiprotons on protons or on neutrons. And you can see that this background doesn't have any resonance structure that could compete with the resonance here, simply because it relies only on misidentified pions. The only way one can get a signal like this is if in a standard model annihilation, one has a pi plus misidentified as a K plus and a K0 recoiling out here, and that masquerades as an S. So this would be the K0 flying off that we don't see. This would be a K plus, this is a pi plus, this is a pi minus. That's the background, and there is no other background in the standard model. So this is a very, very sensitive probe for a very specific dark matter candidate, albeit one that has several interesting characteristics. First of all, it's not surprising that it could exist. This is a standard model system. One knows about 2-quark, 3-quark systems. Of course, tetraquarks have been found, pentaquarks have been found. There's no particular reason why sexaquarks should not happen in the standard model. But more interestingly, this particular standard model dark matter candidate also explains the dark matter to baryon ratio of 4:1. And this is an unexpected benefit of this particular system, which would, if it exists, and if we can find it, and if we can detect it, explain several mysteries at the same time. And I think with that, I've come to the end of my first lecture.
Thanks. So there are questions?
Can you go to slide 13? 13. So there is a mention about laser cooling polarization. So how does this technique work?
So the difficulty right now is to even laser cool molecules at all. You have no way of, or you have very few ways of cooling molecules because they have so many different resonance states in between them. Here, what they're trying to do is to build an asymmetric molecule where really the cooling doesn't happen on the binding energies of the molecule itself, but on the atomic structure of the heavy structure here. Now, once you're able to address the energy levels of that particular heavy atom inside the molecule, then you can manipulate it any which way you like. So in particular, you can also try to orient it with respect to an external field. And this is what the polarization then means, is you're setting up a specific excitation level of that atom inside an external field, or where you then have a orientation dependent shift of the energy levels. And that's basically what you're then doing, is you're only you're aligning those to each other by the transition that you're cooling on.
My question is, in the beginning, you talked about energy resolution of photons. So I was just wondering if the energy resolution has similar precision for other particles as well using these technologies.
So I have to think about that, because what you're trying to measure with these devices, if you're thinking of something other than photons, let's say an electron coming in, is going to depend on whether that single electron deposits all its energy in a single interaction or in multiple interactions. If it were a single interaction, as with a photon, then I would say yes. But for multiple interactions, I think you do not get that anymore, because you have then the statistics of the interactions themselves, and that probably smears everything out dramatically. Now, the energy deposit that we're talking about here is keV. So these would have to be very low energy particles. I'm not sure, I mean, I can't give you an answer. I have to think about this more in detail, but that would be my first approach. For very low energy particles, it might be possible to get that kind of energy resolution. Not useful for high energy particles, obviously.
I was mainly wondering about it because from the last talk, we saw that for neutrino mass experiments, we need something like a sub-EV resolution at keV scale. So
I know that some of these devices are being thought about as used for microcalorimeters, but I don't know enough about that to tell you. I have to think about it.
Very quickly, a question and a comment.
Yeah.
The question was, you showed about these, I don't know, genome, the magnetic field at picotesla. I'm missing something. So like the Earth's magnetic field is several orders of magnitude
It's
above, I believe,
it's a few Gauss, yeah.
microteslas. So
Yeah.
presume, and it's being
Yeah.
sloshed by charged particles and solar storm. So presumably the fluctuations in
No, so these kinds of measurements work. You have to do that in a shielded, in a mu metal shielded environment. You have to get rid of the Earth's magnetic field.
but then how would the external magnetic field penetrate?
So the external magnetic field is not the same thing. It's an axion field that goes through it. That's where you're going to be sensitive to this. I don't think that you need to worry about excluding any with your shielding, excluding coupling to that kind of field. It's a transient. It's not a constant field, and what you shield is really the constant field. At least this is how I understand that experiment.
Okay, maybe we can talk later, but
Yeah.
the comment was mainly when you were talking of your ALPS search. We do look for ALPS in colliders, albeit that we could probably do only up to MEVs, because the Higgs can couple to the
Yes.
ALPS. And because the ALPS can decay to photons, you have no theoretical limit on what mass you can look at the ALPS, just that they will be super merged. So as we build more granular calorimeters, we could go.
So if you have the ALPS coupling to photons and you detect those photons, then presumably you can only get photons that are above your detection threshold.
What we try to do is we try to regress the mass of the ALPS directly from the diphoton cluster. So you're not, so it's like a pi zero kind of a reconstruction that you do. So from the deposit of the two photons, which look super merged.
But so how far can you go in mass? How low can you?
So far, whatever we have done so far, not ALPS, but pseudo-scalars,
Yes,
we could go to 50 MeV. Of course, the sensitivity is bad, but we are working to
go lower, of course, yeah.
So that's the comment.
Yeah. So I guess that has to do with your threshold, your energy threshold inside the detector at some point. Because to see the two photons.
Okay.
Yeah. Okay, we'll do this afterwards, sorry.
Okay, then thanks, sir. Michael again.